All right, so just to talk about, I want to just get to functions, and I thought I'll just introduce random variables and how to kind of create random variables. They're quite nice if you want to simulate data for power analyses or just create an example data set to illustrate things. Okay, so in general, there are a range of distributions built into R, including the normal distribution, uniform distribution, and a whole host of other distributions. Every distribution has kind of the four things you might expect from a distribution. You can get the density of a value, the cumulative distribution, the inverse distribution, and you can generate random data. So think about a standard normal variable with a mean of 0 and a standard deviation 1. We can get the density of the value 1, so that's about 0.24. We can see what proportion of the distribution is less than or equal to 1, so that's about 84%. Or we could look up the value of a particular quantile of that distribution. So, for example, the 0.975 quantile corresponds roughly to our 0.05 level for, say, a Z test. So we could look up, using the QNorm function, that's 1.95. Also, we could generate 5 random variables using the rnorm function. So that's generating 5 values from a standard normal distribution. All the other functions have similar kind of ways of being written. You've got the unif is for uniform, and then once again it's got the density, the cumulative distribution, inverse cumulative distribution, and you can generate random data from that distribution. So to show how this is useful, we could generate 10 values from the normal distribution, and we could actually, each of these things takes particular arguments like the mean and the standard deviation. So I could do a little mini sort of demonstration, draw some data from a mean of 10 and a mean of 11 and show, okay, look, the data's different. So I could get, let's say, a box plot, and we'll talk more about graphic after the break, and there's a box plot with my X data and my Y data. So that's just a quick illustration of how you can use random data. And I'll then demonstrate this more when we talk about functions now. Okay, so one of the great flexibilities, if that's such a word, of R is functions. The great thing about R is written in R, and you can use R to write your own R. So the migration from being a person who uses existing tools to being a person who creates your own software or data analysis tools is gradual, whereas in some other statistics packages, it's a huge leap to going from, say, using SPSS to writing your own macros. In R, it's more a natural extension. So the idea is that you can write your own functions that generalize what you're doing. Here's the most basic function I could think of that just illustrates the basic model of what a function is. It has a name, just like any variable, it has a name. So this is called print some text. And that is assigned from the function keyword. So it tells it it's going to be assigned a function. And then we have the arguments. So this has one argument called x, and it has a default value called hello world. The body of the function is enclosed in braces. And all this function does this time is just print x, whatever x happens to be. In order to use this function, I highlight and run it. So now that function is in my global environment somewhere. There it is. So now I can then write print some text, parentheses, and it runs that function, in this case, with the default argument, hello world. I can also run it with a different argument, like blah, blah, blah. And sure enough, it prints blah, blah, blah. So that's it's a pretty basic function. Let's see if we can come up with something more interesting. I'll start by doing something once with concrete code. This is the general migration pathway. You start doing something with something very specific, and then you say, oh, hang on, I want to do this, but I want to do it for each of my variables. So I want to run it on a different data set, or I want to be able to run it with different variables and different data sets. Or I want to have options, like sometimes I want to remove missing data and sometimes not. So it starts off often with something very concrete, and then you start wrapping it in a function and adding arguments. So this is a very basic statistical power analysis that I run. Essentially, it generates random normal data for two groups, X and Y, which the first group is drawn from a distribution with a mean of 0, standard deviation 1. The second group, a mean of 0.3. So if I was to do a power analysis, like my question would be, well, how often might I say, reject the null hypothesis that these two groups are different? And so this function essentially generates an X, generates a Y, fits the t-test, and looks at the p-value in that t-test, sees whether it's less than 0.05. If it is, then on that particular run of the simulation, we got a significant result. And it saves that value in a vector called significant. And this for loop is a way of looping over this operation 1,000 times. Anyway, not so important about the details of that, but more to the point, if I run all that, it runs that simulation 1,000 times, stores whether it was significant each time, true, false, true if it was significant, and the mean of that is my statistical power. So I had a 21% chance of getting a significant effect. Not much power. So we could convert this to a function. And this is not a very good function. All it does is wraps all that code inside a function and calls it power group diff 1. So all this code is just a copy and paste of above. And you notice that the last argument, statistical power, that's what's going to be returned by the function. By default, you return the last value generated. So if I run this function now, it runs that simulation. Now clearly there's some numerical error because I'm only running 1,000 simulations, so each time it's changing a little bit. But you know, so I've wrapped it in a function. So I can get a sense of numerical error, I suppose. Functions become useful when you can start saying, well, look, I want to run that function, but I want to see what happens if I increase, say, the size of the group mean difference. I could add an argument to that function, exactly the same, but this time I'm going to replace the mean of the second group that it's being generated from with a bigger or smaller mean. So I'll leave the default argument like it was and leave everything else the same, but I've added the argument name has replaced what was a concrete value before. So if I load that function by running it, I can then run this function with different arguments. So what if the mean difference was 0? Well, I have power equal to my alpha. What if the difference was 0.3? That's what we saw before. What if the difference is 0.5? I have 50% power, 85% power, 97% power. So I've generalized the function. I can now apply it. So now that's effectively a power analysis, isn't it? Like, you know, that's cool. I could even, and this is getting a bit more fancy, but I could create a sequence of levels for that mean from 0 to 2, put it in a data frame, loop using what we'll talk about later to get the power for all those levels. Just taking a moment. I'll run it twice. And then I can plot the results. So this is obviously a bit more advanced, but hopefully it's more about inspiring you to say, well, look, okay, there's a power analysis, and I can see the effect of the effect size on the statistical power and make a decision about sample size or something. And then you could go the whole hog and make this function really general by, say, adding arguments for mean of group 1, 2, the SDs, sample sizes, number of simulations, your alpha criterion, and replacing what were concrete values with the argument name. You know, oh, looks like I've done this wrong. I should have put N1, N2. But anyway, the idea is, yeah, you're substituting variable names with argument names, concrete values with argument names, and then you could modify the code and run it in a very flexible way. Anyway, so that's sort of the motivation for functions. You can start with something concrete, put it in a function, and gradually make it more flexible to the point that you're practically making your own packages. If you've got errors in your functions, you can use debugging. So I have a function print some text. If you run debug once on that function, when you run that function next, you'll go into a special debugging environment where you can step through the function and you'll be in a particular local function environment. So you can step through the function, or I often just go back into it and make some changes and so on. If you encounter an error, you can run traceback. And alternatively, you can also put the browser function inside a function, and that will ensure that when you run the function, you will enter the function at that point. So they're just some tools for debugging. RStudio also provides some additional tools. You can also view the source code for built-in R functions. So the t-test code is not very friendly, but the correlation function shows you what the correlation function does. It has an X argument, a Y, a use argument, a method, and you can see all the code for there in it and so on. So you can learn more about R by studying the functions. So you get that if you just type the function name without parentheses. There's a few tricks for functions called methods, but maybe we won't go into that now. You can also view the functions in particular packages if you need to with the colon, double colon. And if there's a hidden function, which some packages hide internal functions, but you really want to get access to it, you can use the triple function, sorry, the triple colon operator. But anyway, yeah, there's a little example to create a function to get some practice in that. So yeah, maybe give that a go.